Hey there, Mr. Stark here with the second lesson in the series. In this lesson titled Calculating Limits, we'll learn about 5 algebraic limiting techniques, one-sided limits, and the sandwich theorem, otherwise known as the squeeze theorem. Grab your graphing calculator, pencil, and paper, and let's learn some stuff. Let's start with a little challenge, finding the limit of two famous functions, sine x divided by x and e to the x divided by x. In just a moment, I'll have you pause this video so that you can find the limit as x approaches 0 of each function. Based on lesson 1a, the first thing you'll do is find the limit of the function numerically using a table, then verify it graphically. Pause now. You're trying it, right? And the answers are 1 and does not exist. If you got the wrong answer for sine x over x, you might have been in degree mode. You have to be in radian mode. Did you happen to enter both functions in and analyze them together? That's what I did. I have 3 calculator screenshots to share with you. In this first one, you'll notice sine x over x in red, e to the x over x in blue, and the change in the x values as you go up and down is 0.1. Notice that the y values for sine x over x are very close to 1. But notice that the y values for e to the x over x are not approaching one number. As we read the table from top to bottom, the y values are getting more negative, and then there's an error, and then it jumps up to 11, and then the y values get smaller. It's kind of weird. In this next screenshot, I changed the table settings. The change in x is smaller at 0.01. The table for sine x over x is really screaming at us that the y value is approaching 1 when x approaches 0. But for e to the x over x, the y values got more intense. We went from -9 to -99, and 11 to 101. As x approaches 0 from the left side, or the negative values, the y values are getting smaller and smaller, a negative infinity type of small. And as x approaches 0 from the right side, or the positive side, the y values are getting bigger and bigger, like a positive infinity sort of big. Finally, I verified what I saw in the table with the graph. As x approaches 0 from the left and the right, the y value for sine x over x approaches 1. If we were to just plug in 0 into sine x over x, we would get 0 over 0. So in this case, 0 over 0 is 1. For e to the x over x, notice that the graph is verifying exactly what we saw in the table. As x approaches 0 from the left side, the y values are getting very negative. And as x approaches 0 from the right side, the y values are getting very positive. Notice that there's a parabolic sort of shape up there. So as x approaches infinity, as we move along the graph to the right, the y values also get bigger. Memorizing these limits might come in handy later on in the course. But if you're struggling a little bit, don't worry, I have a few more examples for you. Next up, some algebra. Let's talk about some algebraic limiting techniques. Basically, how to find the limit of a function using algebra. There are 5 main techniques. They are substitution, factoring, canceling or dividing, conjugates, and common denominator. As you jot these down, I want to point out a few things. First of all, if you're in a calculus course, you should be familiar with these techniques. Second, you might know these techniques but not know the formal name for it. And finally, substitution is the most basic of these techniques. It just means that you plug a number in for x. This can only be done if there are no issues. There's no divided by 0 issue or no even root of a negative number. The example that we'll do involves factoring and substitution. We use the canceling technique in the first example of lesson 1a. For conjugates, remember that the conjugate of something like the square root of x minus 2 is the square root of x plus 2. The first term stays the same, and the second term's sign changes. and I hope you're good with finding common denominators because we're not going to do one together. From the last video, we know that the limit as x approaches 2 of this function is 3. We found that numerically, and we looked at a graph. To take an algebraic approach, let's consider one of these techniques. Let's try substitution. What happens if we plug in 2 for x? Well, in the numerator, everything is great, but in the denominator, we get a 0. That creates a divided by 0 situation, and we don't want that. Let's try factoring then. We have a trinomial in the numerator, so let's see if we could factor that into 2 binomials. Aha! Do you see it? X minus 2 times x plus 1 gives us that trinomial. So that means we have a factor in the numerator and a factor in the denominator that are the same. That leads us to the algebraic technique of canceling, or dividing x minus 2 by x minus 2. So that leaves us with the limit as x approaches 2 of x plus 1. We should use parentheses here to show that we're finding the limit of the entire expression, x plus 1. Since there's no root or fraction, we could simply substitute 2 for x. That gives us 2 plus 1, which is 3. The same answer we found in lesson 1a. That's it. And now that we've found the limit of this function 3 different ways, I have a few general tips for you. When calculating limits of any function, try substitution first. Just plug in the number, see what you get. Then analyze the limit numerically using a table. Verify that limit graphically. Then see if you could prove it algebraically. If a graphing calculator is not available or not allowed, your main approach is using algebra. All of the limits we've calculated so far have been two-sided limits. Now let's consider one-sided limits. There are 2 types of one-sided limits, a left-hand limit and a right-hand limit. The notation for a left-hand limit is the limit as x approaches c from the minus side of f of x or g of x or whatever. C is a real number, and that minus sign is a superscript. The notation for a right-hand limit is the limit as x approaches c from the plus side of f of x or h of x and so on. Again, c is a real number, and that plus sign is a superscript. I'll show you how to find the left-hand and right-hand limits in just a moment. The important thing to note about one-sided limits, though, is that the results of each limit must be equal for the two-sided limit to exist. If the left-hand limit is equal to the right-hand limit, then the two-sided limit exists. Since that was not true for the limit as x approaches 0 of e to the x over x in the challenge, then the two-sided limit did not exist. By the way, if a one-sided or two-sided limit results in infinity or negative infinity, officially the result should be does not exist, since infinity is not a real number. But I think it's really helpful to say that a function approaches infinity or negative infinity because it gives us information about that function. Let's practice finding one-sided limits using this piecewise function. Even though we don't have the equation, we could still find the limits. So here we go. Let's move from left to right. So the limit as x approaches 2 from the minus side, or the left-hand limit, is 3. If we look at x values to the left of 2, they result in y values that are approaching 3. The next one, the limit as x approaches 2 from the positive side. Well, I'll let you think about that while I'll say this one thing about x equals 2. This function is defined at x equals 2. The y value that corresponds to x equals 2 is 3. It's not 4 because there's an open hole there. So the limit from the right side of 2, as we move from the right side to the left side, from the right side, the right-hand limit, as x gets closer to 2 from that right side, y approaches 4. So the limit as x approaches 2 from the positive side is 4. This particular limit can be tricky for students because the function jumps at x equals 2. Remember, the function is defined at x equals 2. F of 2 equals 3. That blue point is a point on the function. The open hole at 2, 4 is not a point on the function. If it was a point on the function, then this function would not actually be a function. It would be called a relation. These fine details come into play a lot in calculus. Since the left-hand limit is 3 and the right-hand limit is 4, the two-sided limit at x equals 2 does not exist. The limit as x approaches 8 from the minus side, the left side, the negative side, as we move along that constant function from the left, x gets closer to 8 and y, well, doesn't really move. It's just 4. Maybe there should be an open hole there at x equals 8, but I purposely did that so that we could see a little variation. So if we say that this is a graph of a function, then f of 8 is 2. We can see that by the filled in hole, and f of 8 is not 4 because you can't have two y values for the same x value. It wouldn't be a function. It would fail the vertical line test. Finally, the limit as x approaches 8 from the plus side, the positive side, the right-hand side. What is that? This is tricky. Some mathematicians might say it's impossible because you can't get arbitrarily close to that point from the right side. You can't let x get closer to 8 from the right side because there are no x values to the right of 8. Some other mathematicians might say the right-sided limit at that point is actually 2, but the two-sided limit at that point is not 2 because we have something else going on to the left of 8. In a formal high school calculus class, students are never expected to answer this question objectively. And for the final concept in calculating limits, I present to you the sandwich. Theorem, that is. The sandwich theorem, otherwise known as the squeeze theorem, allows us to calculate the limit of a seemingly complicated function. Let's use the function f of x equals x squared times sine of 1 over x. The function that we're trying to calculate the limit for goes in the middle of the sandwich. Then we have to think about and choose a function for the upper bound. We're going to call that h of x for high. It's got higher values than the function we're evaluating. Then we think about another function and choose one for the lower bound. We're going to call it g of x for the ground function. The key is choosing functions that we know the limit of so that we could do this final step. We're going to squeeze or sandwich the limit of f of x between h of x and g of x. It's like we squeeze the sandwich to make it smaller and out pops the limit of that complicated function. In this example, we're calculating the limit as x approaches 0 of f of x. But we could also use the sandwich theorem when x approaches infinity or negative infinity. The challenge now is finding h of x and g of x. To do that, let's think about the sine function. What's the max of that function? What's the min of that function? If we don't transform sine of x vertically, in other words, put a coefficient in front of the function like 2 or 5 or negative 3, then the max y value for the sine function is 1, and the min value is negative 1. Since the max value for sine of 1 over x is 1, then the max function would be x squared times 1. Similarly, the ground function would be x squared times negative 1, so negative x squared. We have our original function inside the sandwich, we have our high function as the top bun, we have our ground function as the bottom bun. Now we just calculate the limits. The limit as x approaches 0 of x squared is 0. We could simply substitute because there are no issues. The limit as x approaches 0 of negative x squared is negative 0? 0. Same idea. Since g of x is less than or equal to f of x, and f of x is less than or equal to h of x, then the limit of g of x must be less than or equal to the limit of f of x, which must be less than or equal to the limit of h of x. Therefore, The limit as x approaches 0 of f of x must be 0. There you have it. This wild burger being was just there to help you visualize the sandwich theorem. It was also created by my wife using artificial intelligence. I hope you like it. It was our favorite.